All right, everyone, gather around. Today we're going to walk through a beautiful piece of code that simulates quantum computing. Don't worry if quantum mechanics sounds scary. We're going to break this down line by line, and by the end, you'll understand exactly how this works. Ready? Let's dive in. We are going to cover these 8 parts in our today's tutorial. Part 1. The quantum state class setup. Part 2. Building the full unitary matrix. Part 3. Applying gates. Part 4. Measuring a single qubit. Part 5. Measuring all qubits. Part 6. Quantum gates. Part 7. The CNOT gate. Part 8. Example usage. So, first things first, we're importing number py. Why? Because we need to do matrix operations, and number py is perfect for that. Now, we're creating a class called quantum state. Think of this as a container that will hold everything about our quantum system. The __init___ method is our constructor. It runs when we create a new quantum state. Let's see what it does. We're saying, hey, by default, give me 2 qubits, but I can specify more if I want. A qubit is like a quantum bit, the basic unit of quantum information. This line stores the number of qubits. We convert it to an integer just to be safe. Here's something important. If we have n qubits, our state space has dimension 2 to the power of n. Why? Because each qubit can be in state 0 or 1. So with 2 qubits we have 0, 0, 0, 1, 10, 11. That's 4 states, which is 2 superscript 2. This creates our state vector, an array of complex numbers, one for each possible basis state. We initialize it with zeros. Why complex numbers? Because quantum amplitudes are complex. They have both magnitude and phase. We start in the 0, 0, 0 state, meaning all qubits are in state 0. We set the first amplitude to 1.0, which means 100% probability of being in that state initially. Building the full unitary matrix. Now we have a helper method called _full_unitary_for_single_gate. The underscore means it's meant to be private, just for internal use. This method takes a 2 by 2 gate, like a Hadamard or Pauli-X gate, and builds the full 2 to the power of n times 2 to the power of n matrix that applies this gate to just one specific qubit. Why do we need this? Because when we operate on one qubit, we still need to represent the effect on the entire multi-qubit system. Safety check. We're making sure the gate is indeed 2 by 2. We start with u equal to 1. This will become our full unitary matrix through the Kronecker product. We loop through each qubit position from 0 to n, 1. Here's the key idea. For the target qubit, we use the actual gate. For all other qubits, we use the identity matrix, which means do nothing to this qubit. The Kronecker product. This builds up our tensor product. We're essentially saying, apply this matrix to qubit q and tensor it with all the others. This is how we go from single qubit operations to multi-qubit operations. And we return our beautiful, full-dimensional unitary matrix. Now the apply_gate method. This is where the magic happens. We pass in a gate and a list of target qubits. For now, we only handle single qubit gates. If we're targeting one qubit, we build the full unitary using our helper method, then apply it by matrix multiplication. The @ symbol is Python's matrix multiplication operator. We're literally doing new_state equals u times old_state. We're being honest here. This basic version doesn't handle multi-qubit gates through this method. We'll handle CNOT separately later. Normalization. Quantum states must have total probability equal to 1. Sometimes numerical errors creep in, so we renormalize. We divide by the norm to ensure the sum of squared amplitudes equals 1. The measure_qubit method simulates what happens when you measure one qubit. First, a safety check. Now, we need to calculate the probability of measuring 0 versus 1 on this qubit. The mask is clever. 1 qubit creates a binary number with a 1 in the qubit position. For example, if qubit equals 1, mask equals 0, b10 equals 2. This helps us check whether a particular basis state has that qubit as 0 or 1. We loop through all basis states. For each state, we check, does this state have the target qubit as 0 or 1? The bitwise and operation IDX and mask checks this. Then we add the squared amplitude, the probability, to the appropriate total. We normalize the probabilities. They should sum to 1. This guards against numerical errors. We randomly sample the outcome. Generate a random number between 0 and 1. If it's less than p0, we measured 0. Otherwise, we measured 1. This is quantum randomness in action. If we measured 0, we collapse the state. We set all amplitudes where the qubit is 1 to 0. Then renormalize. This is wavefunction collapse, one of the strangest parts of quantum mechanics. Pulse block does the same thing, but for measuring 1. We zero out all states where the qubit is 0. Measuring all qubits. The measure_all method measures everything at once. Calculate the probability for each basis state, just the squared magnitude of each amplitude. Normalize the probabilities here. Randomly sample which basis state we collapse to, weighted by the probabilities. Convert the index to a binary string. For example, if IDX equals 3 and N equals 2, we get 11. This is our measurement result. The state becomes a definite basis state, all zeros except for the measured state. We return the bit string. Quantum gates. Now let's look at the gate definitions. The Pauli-X gate, it's the quantum NOT gate. It flips 0 to 1 and vice versa. The Hadamard gate creates superposition. It takes 0 to 0 plus 1 divide by square root 2 and 1 to 0 to 1 divide by square root 2. This is the gate for quantum computing. The S gate adds a 90-degree phase to 1. The T gate adds a 45-degree phase to 1. A general phase gate, you can specify any phase angle phi. The CNOT gate. Now the CNOT, a 2-qubit gate. This is crucial for entanglement. CNOT stands for controlled NOT. It flips the target qubit if the control qubit is 1. We create an empty matrix of the right size. For each basis state I, we extract the bits of the control and target qubits using bit shifting and masking. Here's the logic: if the control qubit is 1, we flip the target qubit using XOR. The matrix element uj, I, equals 1 means basis state I transforms to basis state j. A helper function to apply CNOT to a quantum state object, build the matrix, multiply, normalize. Example usage. Finally, the example at the bottom shows how to create a Bell state. Create a 2-qubit system. Apply Hadamard to qubit 0. Now qubit 0 is in superposition. Apply CNOT with qubit 0 controlling qubit 1. This creates entanglement. The result is the famous Bell state. If qubit 0 is measured as 0, qubit 1 will also be 0. If qubit 0 is 1, qubit 1 will be 1. They're entangled. We measure both qubits and see the result. You'll get either 0, 0 or 1, 1 with 50% probability each. Never 0, 1 or 1, 0. That's quantum correlation. And that's it. You've just learned how to simulate quantum computing from scratch. The key ideas are state vectors with complex amplitudes, unitary transformations through matrix multiplication, and measurement causing collapse. Pretty amazing, right? Any questions?